Antenna MCQs, multiple choice questions. Antenna MCQs, multiple choice questions, with answers. 1. Which of the following types of waves are transmitted and received by antennas? A. Mechanical wave. B. Matter wave. C. Microwaves. D. Electromagnetic wave. Answer: D. Electromagnetic wave. Explanation: antennas transmit and receive electromagnetic waves. Electromagnetic waves are a type of energy that transports energy from one location to another. Synchronized oscillations in the electric and magnetic fields have resulted from these waves. An antenna transforms these electrical impulses into electromagnetic waves for transmission and reception purposes. 2. The ability of an antenna to focus its radiated power in a certain direction is measured by which of the following property of the antenna? A. Directivity. B. Impedance matching. C. Resonance. D. Antenna gain. Answer: A. Directivity. Explanation: the ability of an antenna to focus its radiated power in a certain direction is measured by its directivity. Antenna directivity describes how well an antenna concentrates its radiation in a certain direction or region of space. 3. What is the unit of directivity? A. Watt per meter square. B. Decibels. C. Ohm. D. Watt. Answer: B. Decibels. Explanation: decibels, dB, is the unit of directivity. Decibels, in particular, allow us to express a wider range of values. These are the logarithmic units, which are used to calculate the ratio of two quantities. 4. What is the unit of radiation power density? A. Watt per meter square. B. Decibels. C. Pascals. D. Watt. Answer: A. Watt per meter square. Explanation: watts per square meter, W/m2, are often used to measure radiation power density. The watt is a power unit that is commonly used to measure the rate of energy transmission. 1 watt is equivalent to 1 joule per second in general, and when we represent power per unit area, as we do in radiation power density, we use watts per square meter, W/m2. 5. Amongst which of the following is best true about the effective area in terms of antenna theory? A. The effective area measures its capacity to capture or radiate electromagnetic energy. B. The effective area of an item or surface is frequently connected to its physical size, shape, and qualities. C. The effective area of an antenna measures the area which has the least electromagnetic energy. D. None of the above. Answer: A. The effective area measures its capacity to capture or radiate electromagnetic energy. Explanation: the effective area of an antenna is a key quantity that measures its capacity to capture or radiate electromagnetic energy. When calculating the power received or transmitted by an antenna, the effective area is a crucial element to consider. It is usually measured in square meters, m2. 6. A short monopole antenna is a type of? A. A short monopole antenna is a type of resonating antenna that consists of many conducting elements. B. A short monopole antenna is a type of harmonic antenna that consists of two conducting elements. C. A short monopole antenna is a type of horizontal antenna that consists of a conducting element. D. A short monopole antenna is a type of vertical antenna that consists of a conducting element. Answer: D. A short monopole antenna is a type of vertical antenna that consists of a conducting element. Explanation: a short monopole antenna is a type of vertical antenna with a length that is less than a quarter wavelength at the operating frequency. In the horizontal plane, the short monopole exhibits an omnidirectional radiation pattern. 7. Amongst which of the following type of antennas has a length that is roughly half the wavelength at the operating frequency? A. Short monopole antenna. B. Short dipole. C. Half-wave dipole. D. Quarter-wave monopole. Answer: C. Half-wave dipole. Explanation: Half-wave dipole antennas have a length that is roughly half the wavelength at the operating frequency. The half-wave dipole antenna features a symmetrical and donut-shaped radiation pattern and is widely used in television and radio broadcasting, wireless communication, and other applications. 8. Name the region around an antenna where the electromagnetic waves it emits behave consistently and predictably. A. Near field region B. Far field region C. Intensity field D. Radiation field. Answer: B. Far field region. Explanation: the far field is the area around an antenna where the electromagnetic waves it generates behave consistently and predictably. In this field, the radiation pattern of an antenna becomes largely consistent and independent of the antenna's size and form. 9. How many subregions are there in the near field region? A. 5B, 4C, 3D2. Answer: D2. Explanation: the near field region is the area around an antenna where the electromagnetic fields produced by the antenna are still changing significantly. The near field is divided into two subregions, which are the reactive near field and the radiating near field. 10. What information you can get from the power pattern of the antenna? A. Power pattern gives us information about the antenna's directivity. B. Power pattern gives us information about the antenna's gain. C. Power pattern gives us information about the antenna's coverage. D. All of the above. Answer: D. All of the above. Explanation: the power pattern illustrates how an antenna radiates power in different directions. The power pattern reveals information about the antenna's directivity, gain, and coverage in various directions. It is also known as a radiation pattern. 11. An electric field pattern in terms of antenna theory is: A. The electric field represents the distribution of the electric field intensity or amplitude radiated by an antenna in different directions. B. The electric field represents the distribution of the radiation power intensity by an antenna in different directions. C. The electric field represents the variation of the electric current intensity by an antenna in different directions. D. None of the above. Answer: B. The electric field represents the distribution of the electric field intensity or amplitude radiated by an antenna in different directions. Explanation: the electric field pattern indicates the spatial distribution of electromagnetic waves in the far field. It denotes the distribution of an antenna's electric field intensity or amplitude in different directions. 12. Which of the following factors may be adjusted to manage the array's radiation pattern and obtain the necessary spatial coverage? A. Power pattern. B. Electric field pattern. C. Current distribution. D. Array factor. Answer: D. Array factor. Explanation: the array factor describes an antenna array's radiation pattern. The array factor is a system made up of numerous distinct antenna elements that function together. We can adjust the array factor to acquire the required spatial coverage and to govern the array's radiation pattern. 13. Which of the following lobes of an antenna radiation pattern is considered the main lobe? A. Major lobe. B. Minor lobe. C. Side lobe. D. Back lobe. Answer: A. Major lobe. Explanation: the major lobe is the area in the antenna radiation pattern where the radiated power is concentrated and has the greatest magnitude. It represents the primary lobe of the antenna radiation pattern. 14. The lobe that represents radiation in undesirable directions is referred to as: A. Major lobe. B. Minor lobe. C. Side lobe. D. Back lobe. Answer: B. Minor lobe. Explanation: the minor lobe is the secondary lobe in the antenna radiation pattern. It indicates radiation in unwanted directions and has a lesser magnitude than the major lobe. 15. What is the other name of the far field region? A. Fresnel field. B. Fraunhofer field. C. Time-varying field. D. Electrofield. Answer: B. Fraunhofer field. Explanation. The other name of the far-field region is the Fraunhofer field. It is named after Joseph von Fraunhofer. 16. Amongst which of the following field is closest to an antenna? A. Reactive near field. B. Radiating near field. C. Both. D. None. Answer. A. Reactive near field. Explanation. The reactive near field is the area nearest to the antenna, whereas the radiating near field is the area beyond the reactive near field. Field strengths, electric and magnetic fields, are strongest in reactive fields, where they are 90 degrees apart. 17. Which of the following is recognized as the transitional region? A. Reactive near field region. B. Radiating near field region. C. Far field region. D. None. Answer. B. Radiating near field region. Explanation. The radiating near field is known as the transition area because it extends beyond the reactive near field and also serves as a transition between the reactive near field and the far field. 18. Which of the following antennas is designed to give a 360-degree coverage pattern in the horizontal plane? A. Directional. B. Unidirectional. C. Omnidirectional. D. All of the above. Answer. C. Omnidirectional. Explanation. In antenna theory, omnidirectional refers to the property of an antenna that transmits or receives electromagnetic waves equally in all directions. An omnidirectional antenna is designed to give 360-degree coverage and is commonly used in situations where a signal must be broadcast or received in many directions. 19. Which of the following type of antenna has a directivity of 0 dB? A. Horn antenna. B. General antenna. C. Patch antenna. D. Isotropic antenna. Answer. D. Isotropic antenna. Explanation. An isotropic antenna has a directivity of 0 decibels isotropic, dB. An isotropic antenna is a reference point for measuring the performance and directivity of other real-world antennas. We can also say that this sort of antenna is completely idealized. 20. Which of the following factors influences the effective aperture? A. Impedance matching. B. Radiation power intensity. C. Wavelength. D. Scattering area. Answer. C. Wavelength. Explanation. An antenna's effective aperture is wavelength dependent. If the wavelength increases, the effective aperture also increases, and vice versa. 21. Which of the following shows the relationship between effective aperture and the antenna gain? A. The effective aperture is inversely proportional to the antenna gain. B. The effective aperture is directly proportional to the antenna gain. C. The effective aperture and the antenna gain have no relation. D. None of the above. Answer. A. The effective aperture is inversely proportional to the antenna gain. Explanation. The effective aperture is inversely proportional to the antenna gain, i.e., the effective aperture increases when the antenna gain decreases. 22. Unit of the effective aperture is A. Hertz. B. Ohms. C. Radians per second. D. Meter square. Answer. D. Meter square. Explanation. Effective aperture normally evaluates an antenna's capacity to collect incoming/radiating electromagnetic waves. It is influenced by the antenna's physical size, shape, and design, and it is generally expressed in M2. 23. Which of the following condition will lead to higher antenna efficiency? A. Decreasing radiation resistance often leads to increased antenna efficiency. B. Increasing radiation resistance often leads to increased antenna efficiency. C. Maintaining the equilibrium of radiation resistance often leads to increased antenna efficiency. D. None of the above. Answer. B. Increasing radiation resistance often leads to increased antenna efficiency. Explanation. Radiation resistance is a measurement of the power wasted by the antenna as a result of energy radiation. Increasing radiation resistance often leads to increased antenna efficiency. This is because increased radiation resistance implies that a greater proportion of the input power is transformed into radiated energy, resulting in less power being lost. 24. What is the effect of the gain of an antenna on the radiation resistance? A. Decreasing radiation resistance results in increased antenna gain. B. Increasing radiation resistance results in decreased antenna gain. C. Increasing radiation resistance results in increased antenna gain. D. None of the above. Answer. C. None of the above. Explanation. Increasing radiation resistance often leads to increased antenna gain because more power is focused in the desired direction. 25. Which of the following formula is used to calculate the bandwidth of an antenna? A. Bandwidth equals higher frequency asterisk lower frequency. B. Bandwidth equals higher frequency plus lower frequency. C. Bandwidth equals higher frequency slash lower frequency. D. Bandwidth equals higher frequency lower frequency. Answer. D. Bandwidth equals higher frequency lower frequency. Explanation. An antenna's bandwidth is the frequency range across which it can efficiently emit or receive electromagnetic waves. The formula to calculate the bandwidth of an antenna is bandwidth equals higher frequency asterisk lower frequency. 26. Refers to the frequency where an antenna exhibits its maximum efficacy and radiation performance. A. Quality factor. B. Fractional bandwidth. C. Resonant frequency. D. Cutoff frequency. Answer. C. Resonant frequency. Explanation. Resonant frequency refers to the frequency at which an antenna exhibits its maximum efficacy and radiation performance. The antenna responds optimally in terms of radiation efficiency, gain, and impedance matching at the resonant frequency. 27. Is it true that the Friese transmission equation only applies to power received at a distance from a transmitting antenna? A. True. B. False. Answer. B. False. Explanation. The Friese transmission equation is most typically used to compute power received at a distance from a transmitting antenna, but it may also be used to calculate received voltage or electric field strength. 28. Unit of half power beam width is A. Watt. B. Watt. M2C. Decibels. 2D. Degree. Answer. D. Degree. Explanation. An antenna's half-power beam width, HPBW, is a metric that shows the directivity of its radiation pattern. It is the angular width between 2 points on the radiation pattern, and this angle is expressed in degrees. 29. Amongst which of the following shows the relation between half-power beam width and the directivity of an antenna? A. A larger HPBW equates to more directivity. B. A smaller HPBW equates to more directivity. C. A smaller HPBW equates to less directivity. D. None of the above. Answer. B. A smaller HPBW equates to more directivity. Explanation. The antenna's directivity and HPBW are inversely related. Narrower HPBW equates to higher directivity, indicating that the antenna is more focused in a certain direction. 30. Which of the following is true about the first null beam width, FNBW? It refers to the first occurrence of zero power succeeding the main lobe. B. It refers to the last occurrence of zero power succeeding the main lobe. C. It refers to the first occurrence of zero power succeeding the secondary lobe. D. All of the above. Answer. A. It refers to the first occurrence of zero power succeeding the main lobe. Explanation. The angle two spots on the radiation pattern where the power decreases to zero is used to calculate the first null beam width. Nulls are areas of zero power in the radiation pattern. The first null denotes the first occurrence of zero power following the main lobe. 31. Which of the following is true about balun? A. A balun's primary function is to match impedance B. A balun's primary function is to convert between balanced and unbalanced signals C. Both of the above D. None of the above. Answer: C. Both of the above. Explanation: the full form of balun is balanced and unbalanced. It is essentially a device used in electrical circuits to convert between balanced and unbalanced signals. A balun's primary function is to match impedance and convert between balanced and unbalanced signals. 32. Transformer baluns convert between balanced and unbalanced signals using A. Transmission lines B. Transformers C. Passive components D. Integrated circuits. Answer: B. Transformers. Explanation: transformer baluns convert between balanced and unbalanced signals using a transformer. They are made up of two or more windings twisted around a magnetic core. 33. Which of the following baluns utilizes coaxial cables to convert between balanced and unbalanced signals? A. Transmission line balun B. Lumped element balun C. Transformer balun D. IC balun. Answer: A. Transmission line balun. Explanation: transmission line balun utilizes the transmission lines such as coaxial cables to convert between balanced and unbalanced signals. Transmission line baluns are widely used in high-frequency applications. 34. Which of the following balun types employ passive components such as resistors, capacitors, and inductors? A. Ferrite bead balun B. Lumped element balun C. Transformer balun D. IC balun. Answer: B. Lumped element balun. Explanation: lumped element balun is simple to design and uses passive components such as resistors, capacitors, and inductors. These types of baluns are commonly used at lower frequencies. 35. Which of the following is used to inhibit undesired common mode currents in electronic circuits? A. Current distribution B. Current effect C. Current chokes D. Impedance chokes. Answer: C. Current chokes. Explanation: current chokes are electrical circuit components that are used to limit unwanted common mode currents, decrease electromagnetic interference, and improve system performance. 36. Type: one-sleeve balun consists of what type of transmission line? A. Twisted pair transmission line B. Fiber optic transmission line C. Coaxial transmission line D. All of the above. Answer: C. Coaxial transmission line. Explanation: a type one-sleeve balun is made up of a coaxial transmission line surrounded by a conducting shield. Common mode rejection is one of the primary functionalities of the type one-sleeve balun. 37. Which type of balun achieves impedance transformation and signal to balance using looped conductors? A. Sleeve balun B. Folded balun C. Tapered balun D. Infinite balun. Answer: B. Folded balun. Explanation: the folded balun achieves impedance transformation and signal balancing by using looped conductors. The folded balun improves impedance matching and common mode rejection. 38. How many types of linear polarization are there? A. 5B, 4C, 3D2. Answer: D2. Explanation: waves with linear polarization oscillate in a single plane of an electric field. There are two types of linear polarizations: horizontal polarization, vertical polarization. 39. Which of the following is a type of polarization that rotates in the clockwise direction? A. Elliptical polarization. B. Left-hand circular polarization. C. Right-hand circular polarization. D. Vertical polarization. Answer: C. Right-hand circular polarization. Explanation: the electric field vector spins in a circular motion as the wave propagates in circular polarization. There are two types of circular polarization: left-hand circular polarization and right-hand circular polarization. When examined from the direction of wave propagation, the electric field vector rotates clockwise in right-hand circular polarization. 40. A cross polarization occurs when A. Cross polarization occurs when the receiving antenna is polarized in the opposite direction as the broadcast wave. B. Cross polarization occurs when the receiving antenna is polarized in the same direction as the broadcast wave. C. Cross polarization occurs when the receiving antenna is polarized in a random direction as the broadcast wave. D. All of the above. Answer: A. Cross polarization occurs when the receiving antenna is polarized in the opposite direction as the broadcast wave. Explanation: cross polarization occurs when the receiving antenna is polarized in the opposite direction as the broadcast wave. This situation often degrades the signal performance, because of which communication is weakened. 41. Dipole antenna supports polarization. A. Circular polarization. B. Parabolic polarization. C. Linear polarization. D. No polarization. Answer: C. Linear polarization. Explanation: a dipole antenna is often used for transmitting and receiving linearly polarized signals. Waves with linear polarization oscillate in a single plane of an electric field. 42. Which of the following is true about the Yagi-Uda antenna? A. The Yagi-Uda antenna is highly directional. B. The Yagi-Uda antenna is not directional. C. The Yagi-Uda antenna is omnidirectional. D. None of the above. Answer: A. The Yagi-Uda antenna is highly directional. Explanation: the Yagi-Uda antenna is a highly directional antenna, which means that its radiation pattern is focused in a certain direction. The Yagi-Uda antenna is made up of multiple components that are placed in a certain pattern. Metal rods or wires are often installed to a supporting boom or mast. 43. What happens when the number of directors in a Yagi-Uda antenna is increased? A. When the number of directors in a Yagi-Uda antenna is increased, the gain and directivity are decreased. B. When the number of directors in a Yagi-Uda antenna is increased, the gain and directivity are increased. C. When the number of directors in a Yagi-Uda antenna is decreased, the gain and directivity are increased. D. No effect. Answer: A. When the number of directors in a Yagi-Uda antenna is increased, the gain and directivity are decreased. Explanation: when the number of directors in a Yagi-Uda antenna is increased, the gain and directivity are decreased, because adding additional directors allows the antenna to focus and concentrate emitted energy in the desired direction. 44. The H-plane horn produces a narrow beam width in direction A. Electric field. B. Magnetic field. C. Both. D. None. Answer: B. Magnetic field. Explanation: the beam width of the H-plane horn is narrow in the magnetic field direction, H-plane, and large in the electric field direction, E-plane. The aperture shape of this type of antenna can be rectangular or circular. 45. Which of the following is a type of dual reflector? A. Gregorian antenna. B. Cassegrain antenna. C. Lobster back antenna. D. All of the above. Answer: A. All of the above. Explanation: dual reflector antennas are antenna systems with two reflector surfaces that shape and focus electromagnetic waves. There are two types of reflectors in this system: primary and secondary. A primary reflector collects and directs waves toward a secondary reflector. 46. Antennas act as transformers between conducted waves and electromagnetic waves. A. True. B. False. Answer. A. True. Explanation. Antennas act as transformers between conducted waves and electromagnetic waves propagating freely in space. 47. Are high-gain antennas usually used in radio astronomy? A. Reflector antennas. B. Refractor antennas. C. Lens antennas. D. All of the above. Answer. A. Reflector antennas. Explanation. Reflector antennas, parabolic reflectors, corner reflectors. These are high-gain antennas usually used in radio astronomy, microwave communication, and satellite tracking. 48. Coaxial, two-wire, and microstrip are. A. Transmission lines. B. Transmitters. C. Both A and B. D. None of the above. Answer. A. Transmission lines. Explanation. Coaxial, two-wire, and microstrip are transmission lines. 49. An antenna does not radiate uniformly in all directions. A. True. B. False. Answer. A. True. Explanation. An antenna does not radiate uniformly in all directions. 50. A directional antenna can radiate or receive. A. Transmitter. B. Electromagnetic waves. C. Radiation. D. All of the above. Answer. B. Electromagnetic waves. Explanation. A directional antenna can radiate or receive electromagnetic waves more effectively in some directions than in others.